ते एकदा विचारून घे त्याला विचार पाटील साहेब कॅमेरा आलो का एवढे काय होते बोलू
Ojalá 4 empieza.
Sí, pues sí, pero que ya está, voy a probar aquí. Voy a ver.
Is that live? Nice. Broadcasted all over the world.
To YouTube.
एक काम करू का रेकॉर्डिंग मी करू नहीं का उसका एडवांटेज आता है
Just search his name, it should be there. Yeah. Write PhD defense along with it.
You will be live. Not to put pressure on you, but around 7 billion people will be looking at it.
Wow.
You're going to be great.
Let's see.
Focusing easily कर सकते हैं, right?
Mira, tenemos un bolígrafo.
उसका पता है
Me lo voy a llevar. Next time.
How are you? You too.
See it. It sounds more like video. Clear. Yeah,
But I will
the E sounds clear. You said it the first time. You said it first. So
Bhaskar Patil PhD defense YouTube पे search करो.
Well, very learned, very learned. No, serious is very.
Highly and very.
Yeah, highly. The Hulk is highly, Zia is very. So, high is better than. Yeah. To hear as we say.
It has a small delay.
Few seconds.
Yeah, yeah.
yeah, okay.
Yes.
Wow, this is so difficult in this moment.
It will take you maybe to go to the brush of the car and then you will be ready. So this may be 1 minute or intensity. The rest you will manage.
इनको सपोर्ट बहुत इसको with color जास्त with color होप
आम्ही केलं मग आता सेट फक्त आपलं हां सो हे लाईव्ह व्ह्यूचं बटन ना हे दाबलं की मग हे
Dr. Puduri with old classes cannot manage it like that.
लाल वाला वर बटन.
तेच बटन
लाल दाबायचं.
तेच सुरू आणि तेच बंद बटन
Now when you start your meeting
लाल
with
डॉट
Maximum Mobile, you
दिसतो
can
त्याचा आपण सुरू
say, hopefully at the bus.
बॅटरीचं मला माहिती नाही ठीक आहे
and with color be promoted but I don't need to talk to him.
No, very likely. Well, in the beginning, when you ask questions, thank you. Glad to give an overview.
With color I will remember this one.
Best of luck. Hard है ना एक
पता नहीं यार क्या होगा हमारा कैमरा it's good it takes away all the pressure of presenting just keep involved चालू हो
Nice crowd. Well done. There he is. I see him. Oh, dear. No, Theo, I just showed up like this. Oh, 1 centimeter. You should have brought the lady from the store. Sorry? The lady from the store. You should have hired her.
Yeah. So when you switch it on, just remember to switch it on. Everyone switch it on and then
We are last one. Okay, इनका यहाँ पे
Okay, first 2 meters there. 3 and then. I would say just.
What type of feed we should use. So using air is obviously preferred because it is cheaper and it will make the operation much easier. From this experimental runs we can see air plus oxygen performs almost same as nitrogen plus oxygen. Air performs around 20% less than nitrogen plus oxygen, and the selectivity is very much affected by amount of oxygen that is present in the feed. So air with less oxygen produces NO preferably, and oxygen rich produces NO2 more. We achieved almost 2 volume percent of NOx, and the 0D model shows we can go up to 20 volume percent, which is very promising. Second reactor, the directed barrier discharge reactor we used for screening of the catalyst. As I said, we used 2 different reactor types and we screened different supports and the active metal oxide catalyst supported in this support. So what we did, first we investigated support, learn about how they interact with the plasma, what kind of synergistic effect we get and why we get those effects, and then move on to the support size study. That means the best performing catalyst, we use different sizes and then we study for the synergy effect. And finally, the best performing particle and particle size and the support, we pour the active metal on it, and then we study it for the next further intensification of the reactor. So this slide shows the results that we got in the DVD reactor, which was used for NOx as well as for ammonia synthesis, but this shows the ammonia results. So the first graph shows the catalyst support and the particle size effect. The smaller particles gave the highest concentration, and the catalyst support material, which had the high dielectric constant, that performed poorly, but the material with moderate dielectric constant, that performed the best. And this difference in the performance we related to dielectric constant and also the ability of this material to form filamentary or glow discharge. So material which form filamentary micro discharges perform much better. And when we deposited a metal on it, so it also changed the behavior of the plasma, if you see from manganese and rhodium catalyst. Comparing the performance that we got in our reactor with the plasma literature only, we see that our reactor is one of the best. It consumes around 2.8 megajoule per mole. As I said, it produces almost 2 volume% of NOx. With a high-speed imaging, zero-dimensional modeling, and also the voltage current curves, we got more insights in the dynamics of the reactor. And we also know now what is the reaction mechanism, which reactions to be supported and what to be suppressed. For ammonia part, our results are also one of the best in the literature, but ammonia case is not so promising because hydrogen is the expensive reactant. We are dealing with the same problem. So it's not so effective, but still we got quite good results, 1.5 volume% of ammonia that we produced, and filamentary discharges are more favorable for catalyst and DVD reactor combination. However, there should be an intensive screening of the catalyst to explore the whole space. Finally, as the outcome of this project, this container is standing in Germany, in Eindhoven Industries, and it's in the testing phase right now, but it can be further explored for many applications. For example, it can be used for fertilizer production for remote places, such as in Africa. It can be used for hydroponics, for agricultural applications or aquaponics, or it can also be used to store the electrical energy into chemicals, such as in use ammonia as a fuel.
Are you satisfied with this answer?
I'm satisfied. Sounds amazing.
Eindhoven University is always very pleased when other members outside our own universities participate in our committee. So it's a particular pleasure to welcome today Professor Whitehead from the University of Manchester, Dr. Lang from Evonik Industries, Dr. Wang, and Dr. Van Rooij from the FOM Institute Differ. And I would like to request Professor Whitehead to continue the opposition.
Yeah, take a moment. Let me say at the outset that I enjoyed reading your thesis and the work contained in there, and thank you for your presentation, which has summarized the work. I hope you might agree with me that the field of plasma catalysis is a very complex one, and to understand it, as you've been attempting to do, requires a range of disciplines. What do you think those disciplines are, and can you say which you think is the most important in terms of the operation of a plasma with a catalyst?
Okay, Lieutenant, thank you very much for your question. That's a kind remark. Yes, plasma catalysis is indeed very complex field, and it needs cooperation and coordination between many fields. The most important, I will say, starts with physics, then chemical engineering, electrical engineering, and also need a plasma physics in it to really understand what's going on. The surface chemistry is also very important when we have surface chemical reactions. So it's a combination of a lot of fields, and that's the main challenge to understand it.
Okay. If we just unpick some of your work, you in the dielectric barrier discharge work have a lot of results that relate to perhaps the construction of the and the way in which you pack the dielectric barrier and the sort of materials. What would you say that involves? Which disciplines sort of come out in, because you have lots of results that show that the conversion or the reaction yields depend very much on those properties. But what is it more specifically that's being effective there?
While choosing the catalyst for this particular reactions, we thought about the surface properties and the catalyst properties which we typically look into, like the surface area, porosity, and also the acidic or basic sites. But we were not very sure about the dielectric properties, and in the end, dielectric properties were the most important part in the overall performance because it affected the discharge behavior of the plasma reactor. So I will say it's very important to know from a material property point of view, the core properties like the dielectric constant, that those are very important properties.
So it's the support material which is, in your work, the dominant effect. You talk about dielectric properties, but in a sense the material you found to be the best is not characterized by the highest dielectric constant. Can you explain
We tested
a word or two why that is?
Yes, we tested several types of different dielectric materials, and we found out the material which has the lowest dielectric constant are performing better, such as quartz and gamma alumina, and not the high dielectric constant materials such as titanium oxide or barium titanate. This is because the low dielectric constant material influenced the discharge behavior. We saw that from the voltage and the charge curve, that for the alumina support we see a lot of micro discharges forming in the reactor as compared to barium titanate or the titanium oxide.
So when you now put something on top of these supports, in fact in many of your graphs the difference between one material and another, and the difference between having a material and just having alumina by itself, is very, very small in some cases. Did that surprise you? Did that excite you or disappoint you?
Yes, partly surprised, disappointed as well. I was hoping a better results when I quoted alumina with tungsten oxide, for example, and molybdenum oxide, because tungsten oxide and molybdenum oxide are reported to be the best catalyst for NOx formation, and we found completely opposite results, that we are not gaining anything by coating this catalyst. But if you see the ammonia reaction, coating a catalyst on the surface of gamma alumina gave better results than what we got for NOx formation, for example. And I believe it's because of the ease of dissociating hydrogen than easy of dissociating oxygen on the surface.
So, can we identify where the chemistry might be in your work? Can you point to anything which you can say is a specifically chemical rather than physical or electrical effect?
I think in chapter 6, as I said about the different active metals that we deposited, we found out nickel as the best catalyst and the rhodium as well. If you compare the results with only gamma alumina, there we see the enhancement in the concentration of ammonia, and I think that comes purely from the chemical effects, because this nickel and rhodium centers, they are actively dissociating hydrogen which is coming from the gas stream or maybe activated by the plasma. And nitrogen is typically absorbing on the surface of gamma alumina, as reported in the literature. And so the nitrogen which is activated by plasma, it becomes N22 plus, that dissociates on the surface of alumina, and then it reacts with the hydrogen dissociated from these active metals by the surface reaction. And then by step subsequent addition of hydrogen to the nitrogen, we produce ammonia. So this is the reaction that I could say happening.
So would you say that mechanism then is unique to the combination of plasma and catalysis? Could you have a similar mechanism if you just heated up your system?
We tried thermal catalysis as well for the same setup, but we don't see any product formation. So in absence of plasma, there is no product formation. We need plasma for this. And if you just throw nitrogen on alumina catalyst, you will not have nitrogen chemistry option on the surface. You need to activate it need to form N2 plus, and that can be possible only with plasma. And that's I think the first important step what it is happening because of the plasma. Otherwise, if you see the conventional chemistry, that happens around 40 degrees, 400 degrees C, and some 200 atmospheric pressure in Haber-Bosch system, and that we are trying to carry out at low pressure and low temperature.
So one final chemical question, which intrigued me, and that is in both your NOx production and your ammonia production, the stoichiometry that you would write down for the production of NO2 or for the production of ammonia is not what you find when you look for the optimum mixture of the gases. Now, can you explain to a chemist why it should be different?
Sorry, just to make sure, are you talking about the product composition or the feed gas composition?
The reactants, shall we say, the fuel gas composition.
Yes, in case of NOx production system, I got one nitrogen to oxygen ratio of 1 as optimum, which corresponds to NO formation reaction, but we see that NO2 is also formed, and that needs 1.5 ratio as well. And somehow, in case of NOx production with DVD, that's very close, and that matches with the conventional chemistry. But with ammonia, it's completely different. We see a feed ratio of more than 2 as better than conventional of 0.3. And that is because, which I believe is, nitrogen needs to be activated to make ammonia. And this activation of nitrogen is happening by plasma. And if I have more nitrogen in the gas phase, then the plasma forms more filaments, and that's how the nitrogen is getting activated. And the chances of nitrogen getting activated in a DVD reactor are not 100%. We are losing some of the nitrogen. So to compensate that loss of nitrogen which is not getting activated, we need to increase the feed ratio.
So you would say that activation step is the sort of rate determining step.
And that's the most energy demanding as well, because it consumes around 9 electron volt to activate the nitrogen by ionization channel.
Thank you very much. Thank you.
Thank you very much, Professor Whitehead, and the opposition will now be continued by Dr. Lang.
Ja, Professor, many thanks for your presentation. Many thanks for your references to one and the small plant concept. And many thanks for the big work you have done in your thesis. And I want to ask you about your experience in the last 4 years working in such an interdisciplinary area of plasma generation. And can you tell me a little bit where are the hurdles for you to make this work happen in such a good way? And after this, an outlook, what could be a tip for your colleagues in the future to make such interdisciplinary work happen?
Circle is the opponent. Thank you very much for your kind words and the nice collaboration we had over the last 4 years. It was a very challenging project, mainly because of the interdisciplinaries involved in this project. We had to work mostly with the electrical part to get it working. And building a setup, as I said, was the most difficult task and the rate limiting step in my PhD. It took me 2.5 years to build it, mainly because of the different fields involved and generation of the plasma. We built it in 1 year, but it was difficult to ignite the plasma because we did not have the right components to make the ignition, because nitrogen usually needs very high voltage to ignite. And these kind of problems I could have better understand if I had some background from electrical or physics that I missed. And of course, it was not only focusing on the plasma, but it also about catalysis. So I was dealing with catalysis, plasma, and also the electrical part. And also during, I worked on these 2 different reactors, gliding arc and DPD reactor. Gliding arc reactor is highly dynamic. In the first trials of NOx production with gliding arc reactor, we surprisingly found higher efficiency than Haber-Bosch process. and we were skeptical about it, that it's not possible. And then we realized because we don't have the right measurements of the electrical pulse, which I think is the case for most of the literature values as well. Then we went back with the help of the electrical engineers and the physicists from the differ, and then we learned a very important lesson, and we come up with the dynamics, what is happening inside the gliding arc reactor and these two regions. So the learning point for people, I will say, if something is unusual, you should be skeptical about it and try to explore it more and get more insights. Because of the exploration, we went 6 months back in our project, but we come up with a very good understanding of high frequency gliding arc reactors. And that one of the big achievement of my work, I will say.
Can you explain how you solved the problem about analytics of such kind of molecules and such kind of processes?
Yes, I forgot to mention about the analytics. So analytics development also took quite a long time because first of all we were not sure how much product we will produce. In the beginning we started with a calculation of 20%, being very optimistic about it. But we realized it's not possible, and we came to the point whether we will produce even 1000 ppm in this reactor. And that was the most unsure point to decide what I need to do. And then the calibration of NO and NO2 was the next difficult task because they are highly toxic gases and we cannot do that on our own. We need to schedule a different personnel for it, for safety point of view and also for the calibration expert that we needed. We had a very good team. We worked for almost 8 to 9 months having meetings, and then we managed to get it calibrated and move on to that. So analytics is of course very difficult in case of NOx, but in case of ammonia it was relatively easy as compared to NOx. And also we are just measuring NO and NO2 in this project because the intermediate bases like N2O4, N2O3, they are unstable and it's very difficult to calibrate for these bases. There is no calibration mixture available for these bases and they are produced in a very small amount in the plasma reactor.
If you are now looking back about the analytics you applied the past 4 years, do you think there are alternatives in applying and get better look inside the chemical behavior in plasma to analyze it? And do you have had the right tools, or if you have a wish free, what do you recommend for the future?
I think in the last 2 years of my PhD, I used OES and other techniques. But if I could have used techniques like OES to quantify the temperature of the active species and the composition of the species in the plasma phase, that already gives a good idea about where to look into the mechanism. So this definitely is one of the important points to look at. And for other techniques, we try to measure temperature in the packed bed, which we couldn't manage. And the temperature, we were not sure for a long time what would be the temperature. Then we placed a thermocouple, which we were using after plasma was off. And I also started using IR camera. If I could have used these techniques a little bit before, then it would already help to understand the whole operation of the DBD reactor. And same goes for the gliding arc reactor as well. And as I said, gliding arc is highly dynamic. So the whole cycle takes place in 171 microseconds, and detecting the small current pulses needs to be very accurate because I'm calculating power with voltage and current. And in future, whoever is following up, he should be very careful in making these measurements, and that I will recommend as well. One of the most important diagnostics tool for the plasma reactors.
Okay, at the end, you have still one discipline is missing, I think, and that's a team who makes a simulation of the reactor. Can you tell us a little bit more about the things which were simulated and how it will make a link to your results?
For the simulation, as you see from the thesis, it's mostly experimental oriented, but we did have collaboration with Eindhoven University to do the simulation for gliding arc reactor. There we performed a zero-dimensional modeling of the NOx chemistry happening inside the gliding arc reactor, and we got very good insights because of the zero-dimensional modeling. The most important thing that we learned from this is gliding arc reactor is very effective in vibrational excitation of the species, because the energy distribution in the gliding arc reactor is from 0.6 to 4 electron volt, and the simulation shows most of the nitrogen is activated by the vibrational excitation, and that means we can use the Zeldovich mechanism for production of NO, which is very effective way of producing NO rather than producing by ionization, which needs 9.8 electron volt. We can do the same reaction with 3 electron volt, and that is the way to go towards the more energy efficient process, and that we learned from zero-dimensional model. And also we learned about important pathways. For example, if we stop a reaction of nitrogen atom with NO, which is a reverse Zeldovich mechanism, we can produce up to 25% NOx, but just by avoiding it. But it's really hard to avoid this kind of reactions in plasma. But there can be other ways, like increasing the oxygen concentration that will lead to more NO formation. That can be one of the practical solutions. That one suggestion we got. And also the last point about the simulation of gliding arc. We realized that not all the gas is passing through the gliding arc. Only roughly 10% volume is processed in the gliding arc. Still we got 2% NOx concentration. If we calculate it back, we can go up to 20%. The one gliding arc cycle itself produces 20% NOx, which is much higher than what thermal plasma can produce. And this is the advantage which we can bring by doing the zero-dimensional modeling or the simulations. I agree, more dynamic simulations are needed, but it's very difficult to predict how the arc will move because it's highly dynamic.
Thank you.
Thank you very much, Dr. Lang. And I would now like to invite Dr. Wang to ask her questions.
Geachte promovendus, congratulations for your achievement. I think I can say it's not easy for you to work out in 4 years. Very hard work. I think we already had a lot of chance to talk about the details. And I still want to use this chance to have a discussion, either general or details. My first question, maybe a general question. Coincidentally, you are working for reactions on ammonia and NO2. These two reactions are only dealing with two molecules or atoms. And also one of it, ammonia, is exothermic, and NOx is endothermic. Could you maybe give us recommendation which type of reaction you would recommend to select for plasma-assisted gas conversion?
Thank you for your question, and we had a very lot of discussions. Thank you for all your guidance as well. As you see, I worked on the two different reactions. One is endothermic and one is exothermic, and that was the reason as well, to see how two different classes of reaction will work in the plasma reaction for the same purpose of nitrogen fixation. So from the thermodynamic point of view, if you see NO formation, it requires only 6.5 gigajoule per ton of nitrogen. And ammonia, if you go with the hydrogen route, hydrogen produced from the methane, then it needs around 23 gigajoule per ton, which is almost like factor 3.5 to 3.7 difference. So definitely I will say NOx is the best way to go ahead from this criteria point of view. And the second point about the atoms and the molecules, I feel it depends on the type of reactor that we are using. For example, I also did ammonia synthesis in gliding arc reactor, but the product concentration was extremely low, in around 300 to 500 ppm. And that is because for ammonia formation, we need the surface for the reaction, or the surface or the probability to combine these four atoms. And for NO formation, we just need probability to combine N and O, which is much higher than combining 4 atoms. And that's why gliding arc could perform better for 2 atoms, where we just need to combine nitrogen and oxygen, and not for ammonia. On the other hand, for catalytic point of view as well, DBD reactor packed with the different catalyst gave a better synergetic effect for ammonia formation because of the relative ease of hydrogen dissociation reacting with nitrogen to form ammonia. Of course, it's an exothermic reaction, and the DBD heat itself when the plasma is generated. For the exothermic reaction, care should be taken that the temperature is not going too high. We should provide a cooling. If you see in the results, ruthenium catalyst, it declined after the certain power input because the dissociation mechanism activates at a higher temperature because it's exothermic and the reverse reaction starts taking place. So these are the conditions which should be taken into account while selecting a different kind of plasma reactors. And and for the catalyst, I will say the filamentary discharge for nitrogen fixation is important. For other reactions, we are not sure how it will behave.
Regarding the number of items that you are dealing with, if now you are dealing with a system with more items, probably not so easy, like you only get ammonia from N2H2 and you only get NO or NO2 from N2 and O2. But if you are dealing with more complex system, do you still recommend plasma-assisted gas conversion? For example, there are quite some papers, publications on methane-related reforming or partial oxidation. The selectivity of the products is a big issue, I would say. How do you concern this kind of reaction?
Plasma is good to dissociate the big atoms, for example, VOC. So it can be very useful in getting rid of all the volatile organic compounds or the pollutants. But when you want to make a big particles, big molecule with a plasma, I believe it will be not so selective and not so effective. You will end up making more carbon than other products which you don't want.
But methane reforming is not creating big moleculars, it's also small molecular. But how do you control the recombination of all the active species? It's very easy to get active species, but how do you control the direction of the reaction itself?
That usually done in plasma with a glow discharge kind of plasmas in a DBD reactor. When you combine catalyst with the plasmas, that is the usual approach people have adopted. In some cases, you can come up with a catalyst which gives the better selectivity, but usually you don't have any control on plasma reactions in a way that you want. Like in chemistry, we want to get a certain molecule, but in plasma, it is preferred in other way. And then you need a catalyst to change the field and also to provide the surface to have the selective reactions. For example, maybe zeolite can be used in certain cases, something like this.
The common issue for such combination of synergy catalysis by combining plasma and heterogeneous catalysis is high energy consumption. And what's the most obvious advantages then to combine these two way of activate your motivate your reaction?
Yes. When we talk about the catalysis in plasma, we mostly talk about DBD reactors. So I will answer in relation to DBD. DBD has a broad energy distribution. That means most of the energy we are wasting in heating and producing some species which are not useful. So that's why energy efficiency in DBD usually is very low. And sorry, you were.
What's the most obvious advantage? Still, a lot of people are working on the combination of two ways.
It is very easy to screen catalyst in DBD reactor, but if you want to produce smaller molecules like NO, like CO2 dissociation, I think instead of DBD, gliding arc or microwave plasmas are better because they utilize the lower energy distribution of vibrational states. And that is the obvious benefit to go for these two configurations rather than going to DBD. Because DBD mostly not so effective from energy efficiency point of view. It is still used in industry for ozone production, which is one of the big industrial application of ozone. But from chemical synthesis point of view, its throughput is not as high or as easy to control as gliding arc, for example. So I will say DBD has advantage of screening catalyst. More catalyst you can screen, it is much easy to build and operate. But to scale it up, it's better to go for gliding arc kind of reactors.
But do you see the essential kinetics change when you change from DBD to gliding arc?
Yes, there will be complete change of kinetics, I believe so, because the energy, electron energy distribution function will be different for DBD and for the gliding arc reactor. And that is why the different, the energy that we put in the reactor will go into different channels. In case of DBD reactor, it goes more into the ionization channels, but in gliding arc, it will go mostly in the vibrational excitation.
So the scaling up would be there will be a big gap.
Then we should do the experiment with gliding arc and then scale up the gliding arc.
My next question will go to.
Maybe Dr. Warner can make a short final question.
Okay. I would like to ask a question about figure 3.3 on page 68. And you showed the visualization of your gliding arc propagation, and we can see one propagation has a frequency like 17. If I calculate based on 58 microseconds, then the frequency of the propagation would be much lower than the frequency of your power inputs, which you were using 14 kilohertz. Could you explain?
Yes. The figure shows a gliding arc cycle, and one cycle has a lot of pulses that we sent in. And this cycle depends on the gas flow rate and also the power input. So this cycle will be longer if we have lower flow rate and higher power input. So that means we are putting in a lot of pulses, and that is, it depends on the cycle, 58.82 divided by 171 microseconds. That many pulses are put in the one gliding cycle.
Actually, I want to discuss more, but
Yes,
considering the short time, I have to stop.
Yes, thank you very much, Dr. Warner.
Yeah, thank you.
Then I would like to ask the co-promoter of this committee, Dr. Van der Rooij, to continue the position.
Geachte promovendus, let me also first congratulate you with an impressive amount of work done on this thesis, and thank you for a lot of interesting scientific information, which I enjoyed to read. But there are, of course, a few things that we have to discuss today. The last moment, I'm afraid, for this meeting, we have no other opportunity for this discussion, I'm afraid. So let's do it now. I would like first to discuss, when I, let's say, look like this through your thesis, I see many graphs of density as a function of specific energy input. And then I try to decipher the plasma physics that's behind these graphs. And then my trouble starts, of course, because you use as units, you use joules per liter. And I have very much trouble to translate that into electron volts per molecule. But let's not do that translation. And let's first discuss a bit this specific energy input. It's in the end energy per molecule. In your experiments, does every molecule get this average amount of energy that's on your x-axis? Or is there a division? Do some molecules get more than others, or is that different in different experiments?
Very clear, the co-promoter. Thank you for your question, the guidance. Yes, it's a very important question, because when we look in chemical engineering to any reactor, we talk about how much energy we put in per unit volume. And that's the reason I have joule per liter in terms of reactor. And your question about the energy going into the molecule, I think there will be a distribution of energy for different molecules. So all molecules will not have the same energy, but there will be certain kind of distribution, like we showed in our zero-dimensional work, that vibration excitations are the most dominating energy channel for gliding arc reactor. And if you see for DBD, it's more about ionization. So definitely there will not be one energy for all molecules. It will be different for different molecules, and not all the molecules will be activated in the plasma. Some of them will never see plasma.
Yeah, but a minute ago you said in one of your answers to the questions, like if I only consider one discharge in the gliding arc, it's actually performing much better than the overall result suggests. You get 20% of NOx formation in one. So this suggests that there is a huge difference, that some of the molecules get all the energy and others get nothing.
Yeah.
That's unfair.
Yes.
How would you solve that in a gliding arc world?
Yes, indeed, the gliding arc reactor suffers. It performs the best, but it suffers from some of the disadvantages. As you pointed out, very small amount of gas is processed in the gliding arc, and that a very important disadvantage which we can overcome by using, for example, tornado kind of discharge, which has the rotating gliding arc. So the more of the volume will be occupied by the plasma. But still we will not be able to solve the problem. Some of the spaces will have less energy. And also, other option could be to go to microwave plasmas, where the percentage of spaces which see the energy will be higher than the gliding arc, but certainly not 100% for any of the plasma.
Maybe go at a later point. Also, we'll touch upon the vibration excitation, but let me first just go from the back of your thesis to kind of the first graph that I then see, which plots density, concentration as function of specific energy input, and that's on page 173. I try to understand that in a bit more detail from a plasma physics point of view. And I must confess I know nothing about dielectric barrier discharges. The only thing that I know is the biology of field work. So let's try to decipher this. I think Yvonne would not like to know concentrations as function of energy, specific energy input, but would like to know euros out as a function of euros in. How do we get from these graphs to euros?
Yes, indeed. It's from the practical point of view, we need to change the way we plot the graphs. I agree. We need to think from productivity point of view. If we want to show this to the industry, how much tons or liter or grams of product that I am making per amount of energy I am spending in.
Yeah, and
if you plot this graph in another way, in terms of productivity versus specific energy input, or let's change specific energy input with the amount of power that I put in, then all the lines that have, they will have almost the same amount of power going in. For example, the black point, which is on the top for 0.1 liter per minute, will be corresponding to the rate dot for 0.18 liter per minute. So they are having basically the same power going in, plus minus few watts. But the specific energy input is very different because of the flow rate difference.
Yeah, and that's exactly the direction I want to go, and so stop here. Because my next question, and I'm not sure here what I have to do, so we are going to compare the red and the black points that are furthest to the right. You agree, yeah? In this graph, in 173, we compare the most right-hand side red point with the most right-hand side black point.
Yeah.
Because these have the same power input.
Yeah.
They cost Yvonne the same amount of money. But now I'm struggling. Don't I have to multiply the concentration at a factor of 2 in order to get the productivity? Yes.
You need to multiply by the flow rate to this concentration.
Yes.
So you get a productivity, and the productivity will be 1.4 multiplied by 0.1, and this 0.18 by 1.
So flowing the gas faster through the reactor improves your reaction, no?
Yes.
Why?
Because of you stop the decomposition of the products. That is also one of the channels. When you go to higher concentrations, then decomposition of the product will also take place.
Yeah,
and with higher flow rates, you try to stop the decomposition. That's one of the reasons, I think.
Yeah. Another reason could be that because you have different composition, your plasma becomes different.
Different compositions.
Yeah, if you flow slower, you get more products, and the plasma physics or chemistry changes.
That would be one of the reasons as well, because if we see locally, there will be more ammonia molecules next to the nitrogen in case of 0.1. But in case of 0.18, there will be fewer as compared to 0.1.
Critical in time. Then let's go, where is vibration excitation in this thesis?
It's in the modeling part of the.
So yes, in the,
I can explain that.
Yeah. Very quickly, yes, because we have 1 minute.
If you go to the page number 81. There it will say the paragraph in this scheme.
Yeah. That's not your work. That's what other people have said. I have looked it up. There is some vibrational excitation a few pages later. Page 87.
Unexpected.
That's the OES. OES spectroscopy results also.
Yeah.
Also shows the vibration temperatures.
So let me end with a final ugly question. I see kind of a binary code here for the vibration excitation. It's either 5,000 degrees or more than 5,000 degrees in this page. So,
I think
is there now a lot of vibration excitation?
we always work with some kind of error margin, so let's say plus or minus 500 Kelvin, and that agrees with the simulation results as well. The temperature of vibrational spaces will be around 4,000 to 6,000.
I think I'm going to discuss that further with some people who have been involved here. So thank you very much for that answer.
Thank you very much, Dr. Hoogland. I would like now to invite Professor Kroesen to continue the discussion.
Dank u wel. Geachte conference, I would like to ask you about biodata. You are showing the photograph on page 152, where you clearly see that there are spots everywhere on the outside visible of the plasma. There seems to be a homogeneous glow, but I'm pretty convinced that that is not a homogeneous glow, that this is actually millions of small streams. You also say that it is a stream of discharge, so a channel of discharge. Now that I'm wondering how this discharge is propelling, how it is created. What is clear is that you have on the outside you have a mesh electrode in the glass tube. The current cannot get through the glass, it's a dielectric, so it's capacitive transmission, and then you get streamers on the inside. But do the streamers go like a lightning strike through those particles? Do they hop from particle to particle of very short streamers at a time? Do they actually, on one particle, go from metal dot to metal dot? That last is a little bit difficult to imagine because you show a photograph of the particles in one page. I need my glasses for this. 183. 83, yeah. They are photographs of the catalytic particles with the metal dots on it. It seems to be almost conformal, not conformal, but almost covering the whole particle. So what is your view on how is the discharge actually propelling?
Okay, thank you for your question. Yes, indeed, it's very interesting to know how the filament is moving in the DVD reactor. To my belief, the way we proved it, in a blank reactor, that means without catalyst, we see a filament connecting the inner high voltage electrode to the grounding electrode. But when we pack something in it, then this filament try to convert into the combination of surface streamers or surface discharge, and there must be a discharge between particles as well because of the difference in the voltages between the particles. So I believe that the filament converts in the straight filament converts into the combination of shorter filaments and the surface discharges that we can also see from the amount of current ringing we get in the signal for the capacitor voltage. And you asked about the particles on the surface. I think it will not be so straightforward that it just acts on each of the nanoparticles that are sitting on the surface of the support, but it will be kind of random event. Some of the catalyst particles will help to transfer the current, and other will not help in the same filament but in some other occasion. But we also showed from the catalyst testing for ammonia production that if you change the metal on the surface of the support, you also change the plasma discharge. That means this metal also plays a part in the type of discharge we have in the reactor. If you see the figure for alumina and also for the page number 170, you see that different metal has different discharge behavior. For example, ferrous and manganese, they show a continuous flow of current because they are mostly reduced, manganese, and then the current can easily pass through this metal which is highly loaded on the support. If you reduce the loading, then might be you will see more micro discharges because there will not be so much easy flow of current through these particles.
Well, also related to this is if you have a streamer that produces the active species like N2 plus or other unstable species, they can of course fill the volume, and that would make it a volume reactor. And so if you do a radial scaling, so look at reactors of different radius, but keep the peak current constant in the streamers, then you could make maybe a distinction between what is happening in the streamers or what is happening in the volume. If you do an experiment like that, if you look at different diameters.
Yeah, I did use two different diameters in case of NOx synthesis. So I tested a reactor with 22 millimeter internal diameter quartz tube and the 20 millimeter high voltage electrode and the 24 millimeter the quartz tube, and then I changed it to 10 and 6 millimeter respectively. But from the plot, I see that I get almost the same concentration for both the reactors, because I believe it mostly depends on the discharge gap that we have between the electrodes, and in both the cases discharge gap is 2 millimeter, and the dynamics is determined more by this discharge gap. And also the particle that I am using are only 250 micron to 350 micron, so there are usually few particles in between this gap.
Okay, I think we could probably discuss for an hour or so, but there's still the other members of the committee to continue. I'm satisfied for the moment.
Thank you very much, Professor Patil. The discussion will today be finalized by the secretary of this committee, Professor Meijner.
Thank you very much. Geachte promovendus, I would like to congratulate you with your work. I have the pleasure, I'm not an expert in plasma. I start to enter that region a bit, and I enjoyed reading it. And I would like to specifically discuss chapter 4 with you, where you correlate material properties to process performance. And what you do is you investigate a number of different materials parameters, like particle size, particle roughness, to conversion efficiency, let's say. And I was wondering, the different parameters that you investigate, you consider them as independent because you treat them step by step. But to what extent are they independent? I mean, I can imagine that, for example, surface area is also, or let's say surface roughness is also connected to surface area, for example, or particle size. Yeah. So can you say something about that?
Okay, thank you for your question. Yes, these all properties are very much interconnected, but we can separate them for the ease of understanding this phenomenon. For example, you mentioned about the surface area and the sharp edges. We found from our work that plasma doesn't penetrate deep into the pores. So mostly what roughness is matter is about on the surface of the support. So in that sense, we try to compare when we say surface area is about whether the pore volume is used by the reaction or not. And from alpha alumina and gamma alumina experiments, we could say that plasma mostly stays on the surface and penetrates pore sizes more than 15 micron. So if I have pore sizes less than 15 micron, then it doesn't penetrate. similar explanation can be given for different different properties as well. For example, acidic and basic properties that we investigated for the support. For example, alpha alumina and gamma alumina are acidic, and calcium oxide and the magnesium oxide are basic supports on the surface properties. When we compare calcium oxide with the alpha alumina, which are roughly the same surface, we see that this acidic and basic properties of the support are not playing a major role, but it is more dominant by the plasma formation inside this reactor. So we can reach to a simpler conclusions. If you want to make a whole parameter study, then it might take really long time to and need a lot of experiments to do all the parameter variation.
Yeah, I see. And because also, if you then go to one of your figures, where you show the, I think it's figure 4.4. No, not 4.4. It's about the particle. Where you investigate systematically the particle size in terms of conversion and selectivity. I think you hardly there's an area where you hardly see any effect of the particle size, basically. So how do you explain that then? Because it's in you look at particle sizes, and there is the range from 355 micrometer to 1000 micrometer. But basically, all conversions are the same.
Yeah.
So while you say, well, the surface is important, but still you don't see effects of the diameter in that sense.
The trim lines that you are referring to, they are very close particle sizes, and so they are not making so much difference in the particle-particle contact. So the major conclusion that we reach by comparing the smallest particles and the bigger particle is the point-to-point contact between these particles. If you have, for example, 1600 micron particle comparing with 250 micron particle, you will have less point-to-point contact. But if you move to the particles, let's say red line with the green line, they are almost the same, 630 to 500 and 500 to 355. So the particle size are the same. So I assume that void fraction will not change so much. They will be very close. And of course, this is a particle size distribution, and I haven't done a graph for it.
Yeah.
Maybe the higher particle size for one fraction and a lower particle size for the next fraction, they are of this higher composition, and then they match in size more, and that leads to this kind of behavior. That's also possible.
But I think for the selectivity, the differences are more significant, I would say. So apparently it matters for the selectivity. Can you explain that? So why it doesn't matter for the conversion, but it does matter for the selectivity?
Because indeed very surprising to see this kind of different selectivities for the same material. We have the gamma alumina, and it's showing different selectivity. That itself is a very interesting point.
This brings us at the end of the session, so we will re-answer these questions afterwards. And I now request the candidate and the parliaments to take their seats again in the audience. The committee will withdraw for deliberations, and I adjourn the session.
Very nice. Very nice. Yeah, you did very well.
कनाडा नहीं जा कनेडा है अच्छा अच्छा